In this video, we're going to be talking about how we balance some more complex redox reactions, specifically how we balance ones that are occurring in aqueous solution in an acidic aqueous solution. So sometimes we will encounter a redox reaction that, as it is presented in its most basic form, cannot be balanced in the normal way. Which is not the case with the ones we were doing in the previous video. Those you could have just fiddled with coefficients and figured out the answer. But there are some situations where that's not the case. You can play with coefficients for days and you're never going to find a combination that is balanced. And what actually happens in these cases is that because it's happening in an acidic aqueous environment, this reaction is surrounded by water. And because it's acidic, it's also surrounded by hydrogen ions, and it can use that. It can use the water, it can use the hydrogen ions that are present in the solution. Those things are freely available to react as needed. So you can bring in H2O and you can bring in H+ as reactants or products to help you balance it, because that is actually what happens. Those things are consumed and produced as part of these redox processes. So note that we're using H+ here for our acidic environment. We usually prefer to think in terms of H3O+, the hydronium ion, because that's actually what exists in an acidic solution. But hydrogen ion and hydronium ion are effectively interchangeable, and it's a little bit simpler in this context to think about H+. So that's what we're going to use here. But essentially, when you find one of these cases where you can't balance it by the normal method, if you have to balance oxygen, you can bring in water. If you have to balance hydrogen, you can bring in H+. If you have to balance anything else, something is wrong. So those are the only two things that can be solved by this method here. So we're going to be using the same method from the previous video, the half reaction method, to balance these as well, just with the addition of these couple extra steps, that when we get to a point where we can't balance our oxygen atoms, we'll add in some water to fix it. When we get to a point where we can't balance our hydrogen atoms, we'll add in some H+ to fix it. But otherwise, the process is going to be the same. So this is the reaction that we're going to be balancing, the permanganate ion reacting with nitrogen monoxide to produce manganese 2 and the nitrate ion. So just like last time, the first thing we want to do is identify what is being oxidized and what is being reduced. So we will do that by assigning oxidation numbers to all of our atoms and seeing how they change, which one increases and which one decreases, to identify what is being oxidized and reduced respectively. So please pause here and try that on your own. Assign oxidation numbers and decide what's being oxidized and what's being reduced. So if we go through and assign our oxidation numbers here, in our first compound, we have a -1 charge overall that we're going to want to keep in mind. Oxygen generally prefers an oxidation number of -2, and manganese doesn't have a preference, so oxygen can get its way. And there are 4 oxygen atoms in this ion. So we have 4 atoms, each with an oxidation number of -2, and we need to get to a total of -1, means that our manganese atom must have an oxidation number of +7. So I like to kind of do all of the things that are the same element. So once I've done manganese in one place, I probably want to go do it in the other one to see how it's changing. For things that don't have much of a preference, they're likely to be the thing that's changing between compounds. So since manganese doesn't have a preference, I'm going to go look at that next. You don't have to. You could assign them all left to right, and that's fine. But over here, we see manganese with a +2 charge. And since it's just one atom, that means it must have a +2 oxidation state. So right away, we can see that this oxidation number is changing from reactants to products. It's going from +7 all the way down to +2. So that is a decrease, which represents a reduction. So our other reactant here is nitrogen monoxide. Oxygen has a stronger preference than nitrogen, so oxygen gets its way. Oxygen prefers -2. And that means that the nitrogen in this compound must be a +2 in order for our total of our oxidation numbers to come out to 0. On the product side, we once again have oxygen getting its way. Here we have 3 oxygen atoms, each with an oxidation number of -2. We need a total of -1 overall. So our nitrogen atom must have an oxidation number of +5. So we can see the nitrogen is also changing from +2 up to +5. That is an increase in our oxidation number, which represents an oxidation. You will also notice the name oxidation does originate from addition of oxygen to something. So it can be a pretty good clue. This doesn't always work, but most of the time, that if you're increasing the amount of oxygen per atom, here we have like 1 nitrogen to 1 oxygen, and here we have 1 nitrogen to 3 oxygens. You're increasing the amount of oxygen, it was probably oxidized. The name reduction is coming from what's happening to your oxidation number. So the oxidation number is what's being reduced, that it's going from +7 down to +2. You can also see that we're losing oxygen. We are reducing the amount of oxygen. On this, again, they don't always involve oxygen, so you can't always use that. But when it does, it can be a nice little reassurance that your oxidation number assignments were correct. So just like last time, at this point, we can write our half reactions and work towards balancing those. So our reduction half reaction is taking this MnO4 minus and turning it into Mn2 plus. And our oxidation is taking NO and turning it into NO3 minus. So from here, we need to balance these half reactions. So the first thing we want to do is to try to balance these for mass, meaning that we need to have the same number of atoms on both sides of each element. So starting with our reduction half reaction, we see we have 1 manganese atom on both sides, so that's cool, that's good. We have 4 oxygen atoms on the left, and we have none on the right. So this is one of those cases where your normal balancing methods aren't going to work for you here. You can't just adjust a coefficient when it's starting out as 0. So this is where we need to bring in these new ideas that we're going to incorporate elements of our solvent into our reaction. So we need some oxygen. We're in an aqueous environment, so we're going to get that from water. Each water molecule contains 1 oxygen atom. So if I need 4 oxygen atoms, that means I need 4 water molecules. Now, I've created a new problem of introducing hydrogen as well. So I'm going to have to balance for that. I have 2 hydrogen atoms in each water molecule, and I have 4 molecules for a total of 8 hydrogen atoms. Since I'm in an acidic environment, I can add H+ in order to balance that. And I'm going to need 8 of those to balance the 8 hydrogen atoms that I just added on the right. So my reduction reaction is now balanced for mass. I have the same number of atoms of each element on each side. I can move on to the oxidation reaction, where we'll need to do the same thing. So why don't you pause here for a moment and try to balance the oxidation half reaction for mass. So use water first to balance for oxygen, and then use hydrogen ions H+ second to balance for hydrogen. So we currently see that we have 1 nitrogen atom on each side, so that's good to go. We have 1 oxygen on the left and 3 on the right. So note that if we tried to just adjust the coefficients of these 2 things, if we fixed oxygen, we would create a problem with nitrogen, and we don't have a way to fix that. So we just want to add water here to start to fix our imbalance with oxygen. I need 2 more oxygen atoms on the left side. So I'm going to add 2 water molecules over there. I've now introduced 4 hydrogen atoms as well. So I'm going to need 4 hydrogen ions on the opposite side in order to balance that. So that's the only new step in this whole process, is that addition of water and H+ in order to balance our half reactions. From here, everything else is the same. So the next step in our process is to balance these half reactions for charge, and we do that by adding electrons. So remember that we're looking to make the left side and the right side of each half reaction have the same total charge. So again, why don't you pause here and try to do that on your own, adding electrons to equalize the charges. So let's look at what our total charges are currently. Right now we have 8 positive charges on the left and a negative charge on the left. So we currently have a total charge of +7. On the right, all we have for charged things is this manganese 2+. So our total charge at the moment over here is +2. So we see that the charge is 5 units higher on the left than it is on the right. That means that we need to add 5 electrons, 5 negative charges, in order to bring that down. So now, once I've added those 5 electrons in, now my total charge on both sides is +2. I have 8 positives from my 8H+, and I have a total of 6 negative charges on the left, giving me a total overall of +2. For my oxidation, I currently have 0 total charge on the left, and I have -1 and +4, makes +3 total charge on the right. So that means that I'm going to need to bring this charge down by 3 so that these match. Remember that the only way we can adjust charge is adding electrons, is adding negatively charged things. So we're always adding to the higher charge side in order to bring that total down. So now with my 3 electrons, my total charge on the right side is also 0. One other thing to note that can be a little bit helpful is that your number of electrons here is how many your oxidation number changes by. So we went from +7 to +2, meaning we must have gained 5 electrons. So that's why there are 5 electrons here. We went from +2 to +5, which means we lost 3 electrons, which is why there's 3 electrons here. So that can be helpful as well. Sometimes it can be a little bit, I don't want to say misleading, that's not quite the right word, but sometimes it's not as clear if you don't have coefficients in here yet, but that works most of the time, or is a nice way to sometimes check yourself. So at this point, our half reactions are balanced. The only thing left that we need to do is combine them back into our net reaction. But before we do that, we always need to make sure that the number of electrons lost in our oxidation is equal to the number gained in our reduction, which is currently not true. So what we'll need to do is multiply the coefficients in our half reactions to make it be true. So we have 3 electrons given off in our oxidation and 5 gained in our reduction. So the simplest way that we can remedy this is to multiply all of our coefficients in the reduction reaction by 3 and in the oxidation reaction by 5. So we will end up with 15 electrons plus 24 hydrogen ions plus 3 permanganate forms 3 manganese 2+ plus 12 water. And that's going to be the new version of our reduction. And then for our oxidation, we're multiplying by 5. So we'll get 10 water plus 5 nitrogen monoxide forms 5 nitrate and 20 H plus and 15 electrons. So the only thing that matters to us here really is that these two numbers do in fact match, which they do. So at this point, we can combine our half reactions and cancel out anything that appears on both sides. When your reactions are this complex, my recommendation is just combine everything first and cancel afterwards. So remember that we're combining these revised versions. So we will have everything on the left side of this and everything on the left side of this on the left in our net reaction. So we will have 15 electrons plus 24 hydrogen ions plus 3 permanganate plus 10 water plus 5 nitrogen monoxide. And then everything on the right side of both of these on the right side of our reaction. So we'll have 3 is not going to fit. Going down to a new line, we'll have 3 manganese 2 plus 12 water plus 5 nitrate plus 20 H plus 15 electrons. Okay, so sorry, it's a little confusing being on 2 lines, but left side, right side. So anything that appears on both sides, we want to cancel out. So we know going in, we should definitely have our electrons that are going to cancel out exactly. But you will also notice that we have some amount of H plus on both sides, and we have some amount of water on both sides. They're different numbers, so they're not going to completely disappear the way the electrons are. We have 15 electrons on each side, so we can subtract 15 electrons from both sides and they're just gone. They should never be any electrons in your net reaction when you're done with it. But if we have 10 water here and 12 water here, we can take 10 away from both sides. So this will completely go away, and we'll subtract 10 from this, leaving us with 2 left over. Same idea for the hydrogen ions. We have 24 on one side and 20 on the other. So we can completely get rid of the 20, subtract 20 from our 24, and we will have 4 remaining. So our overall reaction, we have gotten rid of our electrons completely. We have 4 hydrogen ions that didn't cancel. We have those 3 permanganate that were not affected by anything. The 10 waters are completely gone, but the 5 NO are still there. Then on the right side, we have 5 manganese 2 plus 2 waters plus 5 NO3 minus. So this is the final version of our reaction. With everything canceled out. So you can absolutely skip this step if you want to and cancel out everything up here is totally fine. Sometimes when there's a lot going on, I just find that people tend to overlook things. I do expect that in a final answer here, everything should be canceled out as much as possible, anything that appears on both sides.